it has been argued that we actually have a refresh rate and that we actually see it there are some people that, if you're outside and you're looking at a fan, there's some people that see it and it looks like the fan's turning backwards because the refresh rate of your eyes is seeing it funny. Most people, though, it's more continuous, and I think it's because the refresh rate of your eye kind of propagates outward and you never really have a moment in time when you see it.
But you can never possibly live in the moment.
I don't know. I kind of think we're more continuous. Or maybe we're discrete, but I like continuous models better because I think they're a better fit for the spatial locality that I think tends to occur in our minds. We certainly are really good at recognizing locality. Yeah, anyway, for right now, let me suggest that this model, there, I'll just call this X and this Y. Usually I go left to right. Today I'm going to go bottom to top because you'll see why in a minute. Here's a basic model. Features go in, labels come out. There you go. But what happens if we add time to this? So let's suppose X is the picture that you see, and Y is, I don't know what you're thinking of the world. That's not very good. Let's do a temporal problem. Let's just do the one we did in the last assignment. X is, nope, let's not do that one. What's something you need information over time in order to predict the outcome? How about words? Let's suppose people are saying a sentence. My mom likes tacos. I guess my mom likes tacos. I'll have to ask her. I think she does. But here's a sentence. We'll write it down. My mom likes tacos. Now, if I feed the word my into my model, can it predict, can it understand what I mean? Can I produce something that's maybe a good response to that? Like, good for her, or something like that. I'm going to claim it can't. We could make a sliding window in which it sees the last n words, so it knows my mom likes tacos, or all the last x minus n things. But then we've got this problem of how big should our window be? Can you learn a pattern that spans several years? For example, you saw your niece when she was 2, and then you saw her when she was 4, and then you saw her again when she was 6, and you see that she's going like this, and you realize, hey, she's getting bigger. She's growing up, right? And humans still can take patterns that occur years apart and extrapolate forward. Or can you detect patterns that occur microseconds apart and extrapolate forward? Sure. For example, watch my finger. Where was it going? It was going that way. And you know, your eye was seeing it here, and then here, and then here, and then here. And was it even discrete? I don't know. But here's what I'm getting at. I don't know what the window is. Yeah.
There's the one thing. So when you look, the reason your eyes move so quick is your brain will actually go back and delete the part of your vision where you're looking.
Probably, yeah.
Because it's a blur. There's factual evidence to support that.
So your eye likes to flit around, kind of does this type of thing. They're called saccades, something like that, where your brain, or sometimes it just kind of flicks over and flicks back. And your mind doesn't sense the whole world jumping around. What happens is your mind knows when it's doing it and compensates such that it's updating different parts of your model. And it enables you to feel like the world is sitting perfectly still, even though your sensors are jumping around, picking up different parts of it. By the way, this is great intro to the next assignment. We're going to use what's called we're going to use a 1 pixel camera, and it's basically going to sample the world by just jumping all over the place, and yet it'll build a consistent model of the world. So, okay. Here's my point. Imagine if this model had information that fed back into it. And it might be that this model is broken up into layers. In fact, it probably is because of the class that we're in. Of course, they're broken into layers. And maybe only the output of this internal layer also feeds back into itself. But this model just got more powerful. And I claim now that if I just say to it, my, well, my can go all the way through and it can predict whatever it wants to predict. But the neural net also has the power to decide what it's computed in this recurrent connection. So it can decide what gets preserved to the next timestamp, right? And then next time, time step 2, I say mom. And now mom goes into this thing. And what's coming in from its memory chain? Well, it decided what goes into it. So now we've got some internal encoding of my plus mom. And it can think what it wants and decide what to remember. And then likes, and it repeats the process. And do you see that it basically maintains its own context here? And because we know that a neural network is a universal function approximator, so it can model an arbitrary mapping, there must be something that's worth remembering when somebody says tacos and previously said my mom likes. There must be something that my mom likes can be encoded as that's worth remembering that will give the word tacos enough context to produce meaning for you, correct? Meaning, and maybe it's just remembering those words, or maybe you've actually already reduced it to some internal representation that to you is the understanding of my mom likes, and you're sitting there saying, your mom likes what? What does she like? And you're just waiting for tacos to come out, and then you say, she likes tacos. That's what she likes. I don't know how quickly the processing happens. Maybe it waits for the final word before we process, but you could, in theory, have the processed version of it recurring, and then when tacos comes in, it knows exactly what to do with tacos. It puts it in the slot of the things your mom likes. If that makes sense? Okay, so I guess what I want to do is prove to you that, in fact, let me prove it this way. I'm going to draw a two-model connection, and I'm going to call this state, and I'm going to call this no controls, and I'm going to call this observations. And we don't have to call them this, but this is what I'm using in the next assignment, so it'll help prep you for it. I'm going to claim that this model is provably sufficient to model any system. And by any system, I mean, in theory, if these neural nets were big enough, this could model the entire Earth, the entire universe. It could model a human being. It could model whatever. And here's my proof. Presumably, there's some state, right? Imagine, let's just do the human being. If you had enough numbers, could you encode your state as a vector such that that vector fully represents everything on your mind, your lifetime of experience, your pose, your posture, the nutritional content inside your tummy, and whatever else defines you? Could your state be reduced to a vector? Probably. I mean, unless you claim humans have non-determinism due to a supernatural component, in which case, no. But for right now, let's pretend humans are deterministic and we can be encoded as a vector. If that's the case, then that vector contains everything you know, right? Somehow encoded in it is your lifetime of experiences and where you think you're standing right now and all that stuff. Well, this vector coming in that I've labeled controls, if it were a big enough vector, it could basically represent all of the sensors that come into your body, right? Every pixel coming in through your eyes, of course they're not pixels, every retinal activation or whatever, every sensor on your skin, whatever your tongue tastes, whatever your nose smells, etc. And because this model, this first one, which I will label transition, if this model transitions from state to state, so you used to be like this, and now you're like that, based on what the world did to you, surely it can map from your previous state to your next state, because this is a universal function approximator. And anything that's a function, this can model. You with me? Okay. Therefore, this first half of the model is sufficient to maintain a changing dynamic state. Well, if that's true, given the state of the universe at any moment, if you knew your location in the world and the direction you were facing and whether your eyes were open or shut and the state of that world, what you actually observe is some function of state, I claim, is it not? Assuming, again, that there's determinism. Well, it follows, therefore, that a universal function approximator can approximate any function. Therefore, this function is enough to predict what you would observe. And presumably, observations come from the world. I guess I should put world down here. And the world produces the... Maybe I have the direction of my arrows bit mixed up. I don't know. But my point is, a model that has recurrent connections, well, let me also point out that if you have two models, with neural networks, two models is the same as one model, is it not? Because they're all just made of layers anyway. You might as well just consider the state to be the activation of some intermediate layer in the neural network. Well, it follows from all of this that a neural network with some recurrent connections, thank you for searching for multimedia plugins for no reason, is sufficient to model any dynamical system, a system that changes through time. Okay, I'm moving a little too slowly here. So whereas a feed-forward function can model any function, a recurrent connection can model any dynamical system. There's another way to draw this system. Okay, let me go back here. Imagine that we have recurrent connections, and now we want to do back propagation. What do? It's hard, right? Because you start back propagating, and some of the connections curl back on themselves, and we don't know what to do. So let's unfold this through time, like this. Such that, actually, I want to get rid of these layers for right now, so I can say it's a general purpose model. Okay. This is a recurrent model that has been unfolded through time, such that this is x sub, well, if this is x sub t, and this is x sub t minus 1, and this is x sub t minus 2, this is x sub t plus 1, this is y of t plus 1, y of t minus 1. Basically, t suggests that this is time right now. And can you see that this is the same model that I had before with the recurrent connections, but it has been turned into a model with only feed-forward connections? It's just that the weights inside of this model are the same. So all of these models have one set of weights, but except for that, over time, I say, my mom likes tacos to the model. And as they feed into this model, it's going to do two things. It's going to predict the output value for right now, and it's going to predict what it wants to feed into the future. And in the future, it's going to get the mom or the likes or whatever the next word was, plus what it decided to remember. And those two inputs produce the new output. as well as what goes into the future. So it's kind of like now the model takes twice as many inputs and produces twice as many outputs, but it's feed forward and operates through time. Yes.
So is xt plus 1 defined by yt minus 1 plus xt?
Depends where you put your connections. So you don't usually take your connection from the past and simply add it to your inputs. You could. But usually you consider it to be a separate set of inputs, and then you do a neural network on it. So you're taking a nonlinear function of your memory and your recent controls.
So